Hi everyone. So we're going to do a summary video of all the rules that we've talked about so far in class in naming ionic compounds. And so there's quite a lot, but we're going to start from the very beginning when we talked about binary ionic compounds. Binary meaning a compound that contains only two different elements, and the names for binary ionic compounds containing a metal that form only one type of ion. So this is the simplest compound of a metal that only has one specific charge. And the rule for writing that name is you write the name of the cation, the full name for that metal, and then the base of the anion plus IDE. So forming the names from these compounds is pretty straightforward, right? Since the charge of the metal is always the same for these types of compounds, it's really not needed to specify any kind of subscript in the compound's name. So for example, MgF2, magnesium is always +2 and fluorine is always -1. So there's no need to call it magnesium fluoride 2 or magnesium 2 fluoride. Those charges are fixed every single time, right? So if we have a formula like CaO, we're going to write the full name for the cation, calcium, which is always +2, so there's no need to put any kind of +2 or number 2 or in the name. And then the root for oxygen is just oxide. Right? If we have Al2S3, both of those ions have only one charge in an ionic compound, so the name for that compound is just the full name aluminum, and then the root for sulfur plus IDE. So again, that IDE ending, most of the time, is the suffix that we use for a binary compound. All right, so when you go to write the formula based on the name, that's when the charge plays a role. So for the compound potassium bromide, potassium is a group 1 metal, so it's got a +1 charge. Bromine is a group 7 nonmetal, it's got a -1 charge. So we only have to put 1 K and 1 Br, and we don't need to put a subscript because the symbol alone represents at least one element, and that's enough of each so that the +1, -1 charge ultimately cancel out. And that's our goal, is to have the charge of both the metal ion and the nonmetal ion add up to 0. So if we have something like sodium oxide, where sodium is a group 1 metal with a +1 charge, and oxide is a -2 nonmetal with a -2 charge, we would need 2 +1 sodium ions for 1 -2 oxide ion. So here their charges are now again going to equate to 0. And then if we have something like zinc nitride, where zinc always has a +2 charge and nitrogen now has a -3 charge, the subscript there is going to require a least common multiple. So this is giving us 3 +2 zinc ions for a total of +6. And this is giving us 2 -3 nitride ions for a total of -6. All right, so if we have polyatomic ionic compounds, it's an ionic compound that contains a polyatomic ion, and they're named using the same procedure that we just talked about, except that we use the name referring for the polyatomic ion as opposed to changing the subscript to IDE, right? So if we have something like Ca in parentheses ClO2 with a 2 on the outside, again, we see that calcium is a +2 charge, and this parentheses is giving us inside it the chlorite ion. And since that already has a unique enough suffix to write the name for this compound, we're just going to call that calcium chlorite. Again, the charge on calcium is fixed at a +2. The charge on chlorite is fixed at a -1. So there's no need in the name to indicate any kind of charge or number or anything like that because the names are always associated with that same charge. So if we have something that's a combination of two polyatomics, here we've got the polyatomic ion ammonium and the polyatomic ion nitrate. The name for that compound would just be ammonium nitrate. Okay, we write the full name for the cation, just like we did with the binaries, and then we just write the full name for the polyatomic ion that it's bonded to. And again, we see that we've got one ammonium, even though there's a 4 there, the 4 is a part of that formula for that polyatomic. We've got one ammonium and one nitrate because it's a +1, -1 compound. All right, when you go to write the formula, again, just like before, we have to focus on the charges. So if we have the name barium nitrate, barium is +2, but nitrate in our polyatomic ion list has got a -1 charge. So we're going to have to cancel out the charges of these two ions by doubling up our nitrates. And whenever we use multiple polyatomics in a formula, we have to house them in parentheses. So this is saying I need two NO3s, and each NO3 or each nitrate has a -1 charge to counteract barium's +2 charge. If we have ammonium iodide, so it looks like we've got that IDE suffix, right? But ammonium is our polyatomic. So ammonium is that NH4 with a +1 charge. And if it has IDE as the ending, then that's just iodine, the element iodine as an ion. So iodide is not part of the polyatomic list. So ammonium here is +1. Iodine in group 7 is a -1 ion. And so we would just write the symbol ammonium, NH4, and then we need one -1 iodide ion to counteract that +1 charge. If we have something like aluminum hydroxide, aluminum is a +3 charge, and hydroxide is that one kind of exception to the one of the exceptions to the polyatomic rule. This is the polyatomic OH that doesn't end in ate or ite, so it kind of hides itself on that polyatomic list. But OH, the hydroxide ion, is -1, so we need 3 hydroxide ions, 3 -1 hydroxide ions to cancel out that +3 aluminum ion. All right, the last one that we're going to talk about is called the transition metal compounds, and this is if the cation could have more than one charge. All right, so we call them transition metals because they can transition from one charge to another. And in this instance, the charge, because it can be different, has to be specified in the metal's name. And this is the important part. We specify the charge with a Roman numeral, in parentheses, following the name of the metal. So when we start to see chemical names that have a parentheses with a Roman numeral in the middle, that parentheses is indicating the charge on the metal, right? So some of these metals are in the transition metal area, but only have one particular charge. We've already talked about these on our periodic table. In group 3, aluminum, gallium, and indium, which are all on top of each other, always have a fixed +3 charge, even though they're kind of tiptoeing near that transition metal space on the periodic table. Zinc and cadmium are always a +2, which are just to the left of gallium and indium, and silver is always a +1. And so we used this image before, and we kind of said we're going to ignore this gray area. All right, so here we've got our fixed +1, our +2, and then there's silver with a +1 charge, zinc and cadmium with a +2 charge, and I'd have you write in on your periodic table that indium is a +3 charge. But all of the metals underneath the staircase, right? So we're ignoring the metalloids, all the metals that are underneath the staircase and this whole gray area over here qualify as transition metals, which means that they could have multiple positive charges in a compound. And so we have to be able to differentiate which charge is actually being used either in the name or figure it out within the formula of the compound. We're going to practice that here in just a second. All right, so for example, copper could potentially be copper with a +1 charge or copper with a +2 charge. So we're going to use a Roman numeral 1 or a Roman numeral 2, and we'll refer to copper 1, or copper with a +1 charge as copper 1, and we'll refer to copper with a +2 charge as copper Roman numeral 2. All right, so now we're going to write the name of the cation, the full name for the metal, the charge on the metal in Roman numerals, and then the same base name of that anion, either with IDE or if it's a polyatomic with the 8-ite ending of that polyatomic. So if we have iron FeCl3, we would see that iron has a charge of +3 because it's bonded to 3 -1 chloride ions. And so we would name this iron Roman numeral 3 chloride. All right, so we have to do a little bit of backwards thinking to figure out, based on what it's bonded to, what would its positive charge have to be. So let's put this into practice. We've got the formula PbCl4. And so just like the iron example from before, if this one lead ion is bonded to 4 chloride ions, and each Cl is a -1 charge, then that lead has to have a positive charge of 4. So we would call this lead Roman numeral 4 chloride. If we have a lead bonded to just one oxygen ion, and oxygen always has a fixed -2 charge, then this one lead has to be +2. So for this, we would call it lead Roman numeral 2 oxide. Right now, I want to point out that the Roman numeral does not always match up to the subscript of the nonmetal. Here it did, but down here it does not. We only have one oxygen, we only have one lead, and a lot of times students get a little misled and they want to call this lead 1 oxide. But again, that Roman numeral has to tell us what is the charge that metal has to make this whole compound add up to a total sum of 0. Okay? All right, so how would we write the formula if we're given the name? Here it's chromium 2 chloride. So the name is telling you that this chromium behaves with a +2 charge, and the periodic table tells us that chloride is -1. So this would be CrCl2, 2 -1 chlorides. Here again, the Roman numeral is telling us that tin is behaving with a +4 charge, and oxygen on the periodic table has a -2 charge. So if this is +4 and this is -2, I'm going to need 2 oxide ions for that 1 +4 tin ion, so SnO2. And then lastly, if we have a +3 iron and a -2 oxygen ion, we're going to have to factor in that least common multiple of 6. So we can go iron 2, 2 +3s, and 3 -2s, or 3 oxide ions. Again, the Roman numeral tells us that charge. So if I have 2 iron 3s, then that's a total of +6. And if I have 3 -2s, then that's a total of -6, and those charges add up to 0. All right, so now let's just do some overall practice because we got to be comfortable whenever all of our rules are mixed together. So what are some of the things that we have to start asking ourselves? First, I would say, is calcium a compound, or is calcium a metal that has one charge or multiple charges? If it's in group 2, then it has to be +2. And then do we have more than 2 elements? Is this binary or is this polyatomic? I've got calcium, sulfur, and oxygen. So if I have more than 2 elements, then there has to be a polyatomic. So the name for this compound is just calcium sulfate. Again, we don't need a Roman numeral, but the base rule is to write the full name for the metal and then the full name for the polyatomic, which is sulfate. And if we've got CuPO4, copper is not an element that I can tell its charge based on its location. It's in the transition metal block. So I have to look at the fact that it's bonded to this phosphate polyatomic, which has a -3 charge, and there's only one phosphate ion. So then this copper has to be +3. So I would call that copper 3 phosphate. All right, so when we have to derive the formula based on the name, the transition metals stand out because they're the only ones that have a Roman numeral connected to them. So a little bit of the work's done for us. Here we have chromium with a +3 charge. We need to look on the periodic table. We've got nitride, and that suffix is also telling part of the story. So if this has an IDE ending, this is binary, so there should only be 2 elements. So there's no polyatomic involved. So if chromium's +3 and nitride by its location on the periodic table is -3, I only need one of each, so CrN. If I don't have a Roman numeral, then the metal's charge has to be derived from the periodic table. And again, we've got that IDE ending, so then this has to be a binary ionic compound. So if sodium is +1 and oxygen is -2, we need 2 +1s and 1 -2. And then lastly, we've got iron 3 hydroxide. And again, this is that one that kind of hides itself as a polyatomic. So this is both a transition metal and a polyatomic ion. Iron is +3. Hydroxide as that polyatomic OH ion is -1. So I need 3 hydroxide ions to cancel out that 1 +3 iron ion.